Enzyme doesn't care. Whatever it has more of, it'll go in that direction. So if we have more acetoheptulose 7-phosphate, and if we have more I guess it's always, what am I doing? Where's my other aldehyde? I guess just that. So if we have acetoheptulose 7-phosphate, we have lots of this and lots of this, the reaction goes that way. If we have lots of this and lots of this, then the reaction goes this way. It's freely reversible. It only depends on what we have more of. So what we have in here, right, all that can freely equilibrate. Jenny's still not happy with my answer.
I'm going to have to think about that. I'm not understanding how, on the bottom, yeah.
What
that,
this eliminates?
When up on the upper right, the other bond is being broken.
Because
Isn't
this
that,
one is, we have to remember, this is an equilibrium reaction. So when this gets to here, if there happens to be glyceraldehyde phosphate around, it goes this way. If there doesn't happen to be a glyceraldehyde phosphate around in time, it just goes back. So this part of the reaction is reversible in the same way this part of the reaction is reversible. We just tend to think of it in this direction because most of the time we're feeding in this as we do the pentose phosphate pathway. And so since we're feeding the process this, it tends to push it all this way. But if we create a situation where we took a cell and we put in lots of acetoheptulose 7-phosphate, it would go that way. That drew stunned silence from the crowd. It's a mass action issue. We give the system lots of this and lots of this, so we tend to think of it going that way. But that's not, it can go either way. The only reason we draw it this way is because we tend to take this and do something else with it. And by doing something else with it, we take this out of the equilibrium, which tends to keep things flowing this way.
I understand the equilibrium part.
Yeah.
I just don't understand why you wouldn't end up with a 6 carbon, because the bond that would break in the intermediate right before that would be the one alpha and beta to the
This one?
Yes.
Well, then you would end up with a 1, 2, 3, 4, 5 carbon intermediate. If this broke, you just go back to there.
Okay.
Right? You get those 5 carbons back.
Okay.
Okay. Does that help? Yeah?
Why did you go elimination on that one? But then carbonyl substitution.
This one here?
Couldn't you go elimination on that one?
Sure. But if we did elimination on this one, we would just go back to our original starting material. That happens. Right? This step is in equilibrium. So if we put a bunch of the enzyme in and we put a bunch of xylulose 5-phosphate in there and didn't give the enzyme ribose 5-phosphate, it would just keep doing this back and forth. Because it would get to here and it wouldn't be able to do anything, so it would just go back. Right? Each one of those steps is reversible. Question, Devin?
I just have a question about the 3 reactions. Are they like sequence reactions? Because the first trans ketolase gives like some of their products, some of the reactants in the next one. So do they kind of go in sequence? Not to like a full extent where like, oh, if you skip one, it wouldn't go.
They do, except, and this is where we have to be careful, and this is where the stoichiometry gets to be an issue. And this is where we have to think about the stoichiometry. Because if we just think about 2 of these, we've got 5 carbons and 5 carbons makes 3 and 7. Good. But now the 7 and the 3 make a 4 and a 6. Good. Problem is, now we're out. We just used these 2. So now we got to take this 4. We got to bring in another xylulose. This one has to be a different one to get this 3 and 6. Does that make sense?
So there needs to be like pools of all the
There
reactants
needs
and
to be-
products at all times.
Exactly.
So those just kind of affect the equilibrium of the other reactions?
Right. That pool of 5 carbon phosphates is constantly adjusting its equilibrium to replace whatever these reactions are using. Okay? Okay. Now, if we want to look at the trans-aldolase reaction, the trans-aldolase reaction occurs really very similarly to the aldolase reaction. If you remember, right, the aldolase reaction used a lysine as a nucleophile to make an imine so that could hold this structure specifically in the enzyme. And it used the imine to make the alpha-beta bond labile. So we do the same thing. The only difference is, as I said, right, this leaves as a carbanion. Right? This is showing the carbanion form in equilibrium with its enamine form. Right? The carbanion form, instead of simply being protonated, uses the aldehyde as the Lewis acid. It completes a nucleophilic addition, and then we undo making the enamine. Right? We hydrolyze the enamine, or the imine. We hydrolyze the imine to go back to the carbonate. So we've really got the same question here, although it looks a little less complicated. Right? We've got that same situation here where if we go this way, we're making an imine. If we go this way, we're making an imine. So in general, this enzyme, right, all it does is it uses its amine as long as it's dealing with a ketone sugar that can get in that active site. It attacks and it will transfer 3 carbons. It doesn't care. Okay? Does that help? I've put you guys in stunned silence way too often today. Melanie and Brooke are going to be nervous when they look at this. Okay? So. Yep, we've done all that. We've done all that. We've done all that. Okay. So, there's the stoichiometry we were talking about. It takes at least 3 5-carbon sugars to end up with 2 6-carbon sugars, fructose 6-phosphate, and glyceraldehyde 3-phosphate. All of which can go back into the glycolytic pathway and either continue down glycolysis if we need the energy, or go back up through gluconeogenesis and make, in essence, 2.5 glucoses. That's why I think it's easier to consider 6 glucoses going in, and essentially we can get the equivalent of 5 back into glycolysis or gluconeogenesis. Questions about that? Kyle's been quiet today. We're good? We're happy to be part of this plan. So, let's look at different ways the pentose phosphate pathway can be used. Because we've talked about the pentose phosphate pathway being used specifically for making NADPH, assuming all the carbon skeletons get put back into glycolysis. That's not always the case, because we can use the ribose 5-phosphate in nucleotide synthesis. So the simplest way of looking at this is, say we are in a synthetic mode, a biosynthetic